right, so today we're going to take a look then at single displacement reactions. Single displacement reactions and the activity series, whatever that means. And this again is a topic that you should have covered in grade 10 science, but we're going to expand on it for grade 11. We're going to understand it a little bit more deeply. And I should say that there is something, thank you very much, there's an instructive element to kind of using metaphors. So if you imagine that a synthesis reaction is almost like sort of, setting two people up on a date. So you've got two people here, and if all goes well, next thing you know, they're a couple. Next thing you know, they go everywhere together. They start laughing at the same jokes, watching the same TV shows. You never see one without the other. Does that make sense? You take two things that were formerly separate, you put them together, and now they are connected. Now they're together. You can imagine synthesis reactions as a dating service. If that's kind of the analogy we're using, what would we think of as a decomposition reaction? What would the analogy be there?
Two people breaking up.
Yeah, breakup. Divorce feels darker to me for some reason. I like to keep this light. But sure, yeah, by all means, you had these two and they were inseparable. They went everywhere together. They went to the mall together. They went to the movies together. They went to school together. Wow. Oh, geez. God, I was just going to say that they were like, I don't know, they kind of grew apart and they respectfully passed ways. But okay, no, Preston has given it to us. And then calcium found out about nitrogen's duplicitous ways and had been carrying on behind their back without them knowing it the whole time. Wow. Yeah. You guys have like a thirst for drama. Wow. It's divorce. It's infidelity. It's very... I was just like drawing stick figures here, but it's getting intense. Well, anyway, so if synthesis reaction is, successfully getting somebody to date you, if decomposition reactions are that person discovering all of your many faults and leaving you, today we're going to talk about single displacement reactions. And if we carry on with the metaphor, what's a single displacement reaction? Well, since we've gone dark here, let's feed in. But let's say we had, our friends here, and they're a couple. They go everywhere together, and they're on a date. And I don't know, where do you take a nice date? Wendy's. Wendy's, like really, wow. We're stepping out tonight, baby. We're going to Wendy's.
Not McDonald's anymore.
We're walking through the drive-thru. That's right. Maybe we'll get 2 Frosties and like dip our fries in them. Oh yeah, like we're talking romance. Okay, so they are romantically going through the drive-thru, and like Blue Guy's been thinking lately, Green Guy's really nice. I like Green Guy a lot. This is a good relationship. It's not very exciting. Wendy's every week, Wendy's date. And then who do they come across?
Red Guy.
Oh man, they were into Red Guy. And Blue Guy just can't help but thinking, oh, Red Guy. Something about Red Guy. I don't know. I don't know what it is. So then what happens? What would be the worst case scenario? You take your beloved, this person for whom you care deeply, you take them to Wendy's. What is the worst thing that could happen on your date at Wendy's? Yes. No. By the time. Okay, well, outside of like. Preston would bring up domestic acts of terrorism. I was thinking like from a date perspective. You go to Wendy's and by the end of it you have nobody but Wendy because all of a sudden Blue Guy's like, Green Guy's very nice, but Red Guy's real exciting. And before you know it, Blue Guy is leaving with Red Guy. Oh, that's Pink Guy. We haven't even met Pink Guy yet.
That's right.
Yeah, he's an entirely different person. And now, poor Green Guy, all alone. All right? If if synthesis teaches us, how to come together, decomposition teaches us how we come apart. Single displacement shows you that don't go places where, more attractive people than you are with your date. You don't want to do that. I'm kidding. That's a joke. Or is it? But anyway, yeah, it shows you a date gone terribly wrong. You leave together, and by the end of the night, the one with whom you were together has left with someone else. Isn't that always the way? And this is single displacement in a nutshell. If you can understand dates gone bad at Wendy's, then you understand chemistry. There's really two things you need to know to be good at chemistry: Lego and unsuccessful romantic relationships. And I get both of those perfectly well. So, let's take a look. A single displacement reaction is one where a compound and an element react and the element trades places or displaces one of the species in the compound. So they look like this. If we have some reaction AB and they react with some other thing C, what we get by the end is
ACB.
A, C, and B by itself. And obviously, depending on the type, it could be the first thing that is replaced or the second thing. I'm actually going to suggest that in this class, I'm going to write CB plus A, not because your answer was wrong. Your answer was not wrong. It was just as right as this, but because more of the reactions we do in class will look like this, which is to say more often than not, we're going to be replacing that first compound, or that first species, and we'll talk about why that is.
Why did red guy start with blue guy, not green guy anymore?
Well, this is like green guy's revenge. Green guy went out and bought an expensive car, because that's how you impress girls, is just with material things. I understand this.
Blue guy back.
And that
Sorry?
red guy.
I'm confused. Listen, I can't keep that. These are elements. These were people. These are elements. Just because two people are the same color doesn't mean they're the same person. Good Lord. Let's focus in. You'll notice that these people had legs and these people just have compound curves. Anyway. Yeah, they're totally different. Anyway. So a single displacement reaction looks like that. So let's take a look at an example. When solid magnesium reacts with copper 2 sulfate. Okay. What's solid magnesium? That's easy. What am I going to write here for solid magnesium? Yeah, MgS. And what would that look like? Well, it would look like a piece of... Yeah, it looked like a piece of metal. It's going to be magnesium ribbon. Magnesium alloy, something like that. Okay, and what are we reacting it with? Oh man, what's copper 2 sulfate? And a reminder that 5,000 times a week, you're going to come over here and say, okay, well, when copper 2 has what charge? Positive 2. That's what the 2 tells you, right? Does it tell you that there are 2 coppers? No, it tells you the charge. And what is sulfate? Does anyone remember off the top of their head? We can look it up if no one does.
SO3.
Close. That would be sulfite. SO4. Sulfate's one of the weirdos that has 4 oxygens. Does anyone remember its charge?
Positive 1.
-1.
It is negative... It's negative 2. Sulfate's negative 2. By the way, if you don't have that memorized, that's okay. Where could you look it up?
Which one's one that's negative 1?
Periodic table, right? Like the periodic table I gave you has its little list of common radicals. You've got it right there in front of you. You could Google it. It's okay. Lots of resources. Now, if we had one of each of these, what do we notice? Yeah, the charge is balanced. So the formula of this thing would be?
CuSO4.
Good. By the way, see how I just did that to get the formula? That's what you got to do every time. All right? If you're not doing a step like that, either by writing it down or doing it mentally, and you're just randomly bashing things together, you're not going to get the right formulas. You have to actually take the time to work out the formulas. So, magnesium reacts with copper 2 sulfate. By the way, copper sulfate by itself is just a powder, but that's not usually how we do a reaction. Am I going to take a piece of metal and then sprinkle a powder on it and wait for it to react? I mean, I guess I could. But more often in chemistry, how do we do these reactions? We'd get a test tube, and what would we do with this stuff? We would probably... I heard it. Someone said. Ooh, maybe, but we'd probably take this and dissolve it in...
Water.
In water. And how would I indicate that we've done that?
AQ.
Yeah, AQ. You don't have to, by the way. You absolutely could like sprinkle it on and heat it up. But if you want to make sure that copper sulfate's touching every possible surface of that magnesium, dissolving the copper sulfate in water is a good way to do that, because then you can just dip the magnesium in. Does that make sense? So as often as not, we dissolve that and we use the AQ to show that it's been dissolved. Okay, so in this case, magnesium will take the place of what? What is it going to displace? Magnesium is going to switch places. Copper and sulfate were on a date. They went to Wendy's. They're getting junior bacon cheeseburgers off the value menu, the small fry. Then you get the Frosty, and you dip those in. They're having a good time. They're just having a nice time. Copper has no idea that magnesium is on the way, and what's going to happen?
Oh, magnesium's gonna kill copper.
Oh, it's going to kill it. Wow. I just thought it was going to say, hey, junior bacon cheeseburger, I've got the Baconator over here. And sulfate was going to swoon. But okay, I see this as murder most foul. Fair enough. Magnesium will take the place of copper. Magnesium is going to kick out copper. Does that make sense? So now, on this side, what will be by itself?
Cu.
Copper. And what will it look like?
Cu.
Like, will it be Cu2 plus? Will it be Cu solid? Will it be Cu liquid? What are we looking at?
Cu solid.
Yeah, very good. No charge, because copper may get kicked out, but it has its dignity. It takes its electrons with it. All right? All right, it's going to be solid copper. And now, what will be the compound? So copper is now alone. And then magnesium forms a compound with sulfate. Now, can I just assume it will be MgSO4? I think as it happens, it will be MgSO4, but can I just assume that?
We can assume it, but you know.
What do I have to do?
Check the charges.
I've got to check the charges every time. Every single time. 1 billion times. What is the charge on magnesium?
+2.
Yeah, what's the charge on sulfate?
-2.
And so we happen to know then that the formula will be? Yeah, they balance. So this one happens to be a nice easy one. But do I get to always assume it will be a nice easy one? You have to check every time. You have to check every time. So MgSO4. And I happen to know that sulfates dissolve in water, so I'm going to put that as aqueous. Aqueous. If you didn't know, well, it's okay. You can just leave it blank, because you can't know things you don't know. But I know about sulfates. Sulfates dissolve in water, and since the copper with sulfate was dissolved in water, there's lots of water around, so that's going to give us magnesium sulfate. We're going to do some reactions like this tomorrow. Maybe the day after. Probably tomorrow. And it's kind of cool, because you start with, like, magnesium and a blue liquid, and when you're done, you've got a piece of copper metal in the bottom that you didn't have before. Kind of a cool thing. Like it came out of nowhere, but it didn't come out of nowhere. It came out of the solution because magnesium kicks copper out of that solution. Does that make sense?
Sure.
All right, like displaces like.
That's
Positive ions can only replace positive ions. Makes sense, right? Which in general means metals replace metals, but really it's more complicated. Well, it's not more complicated at all. Really, it's just more general. Any positive ion can only be replaced by a positive ion. Any negative ion can only be replaced by a
negative ion.
negative ion. That's it. That's the whole thing. I don't really know what the relationship example of that is. I guess, I don't know, if you're dating somebody. Yeah, of course you can. All right, so I want you to try a couple. Well, I want you to try one. Iron and silver nitrate. Iron and silver nitrate, right? A balanced chemical equation. What will happen if I put iron and silver nitrate together.
What iron? Iron?
And you can assume any compounds will use iron 2 plus for now. Okay? Does iron have a charge when it's on its own, by the way?
No.
No. I pick up a piece of metal, it doesn't shock you, it's not charged. But when it forms a compound, for now you can assume it will be Fe2+. The truth is you'd get two products. You'd get some iron 2 and some iron 3 product, but we'll keep it simple for the time being. Oh, and then I gave you a question but no space after it. That was clever. Oh, you have a bit of space. I just don't have space. I'd like you to do both of these, if you could. Because one, we have a metal replacing a metal. Here we don't have a metal replacing a metal. Anyway, you'll figure it out. So take, what do you think, 7 minutes and work those out? And don't wait for me. Work them out. If you don't know what to do, that's okay. Talk to the people around you. Be a team. All right? Be a team. Get it done. Yeah?
Can you do the stuff in the notes?
I can. How's that? Can you see that?
Yeah.
Great.
Silver just has charge +1, right?
I'm pretty sure. Check your periodic table, but yeah, Ag is +1, I think. Like I think it's. I know it's +1. I think it's only +1.
Yeah, no,
I shall return. And Jonesy, where are we at? Amazing.
And I have to write down my hours, but I
Oh no, that's okay.
said she was gonna write down all my hours.
She's running class now. But then you and I are going to share one calendar and just set dates.
Okay, my class is.
Cool. No worries. Cool. Yeah. No worries. So, can I ask, is it online for everyone?
Yeah.
It's online for everyone. Okay. So it's not like you're being beamed into a class. It's happening with people physically in it. Cool.
You didn't notice that.
You got it.
Speedrun.
Like hard way to like the OD on Zoom called it, like the lowest death rate.
Fastest. Not if I fall asleep on the sleeping customers fall off. Fastest wake to sleep speedrun percentage. While sleeping goes down.
Spring a length of rope in the class.
Yeah. Gallons are supposed to snap me up. Yes, I know what they're supposed to do. You fucking orange sheets. Shit, you look like you were. God damn, you crazy motherfucker. I don't care about me. Others are prison. You were no idea.
which is also nice, right? It's feedback without the hand cramps. I like it. Okay. I went to help scorekeep the boys basketball game yesterday. And a bunch of grade 10s playing.
And the school?
Sorry? Yeah.
Hey, we have a basketball team?
Oh yeah.
Oh, how come I didn't sign up?
Why don't you listen to announcements, man?
It's volleyball, not basketball.
And then volleyball.
I'm sorry. Volleyball. Did I say basketball? Yeah. Girls are playing basketball. It switches though. Why don't I listen to announcements? We will have a basketball team though. It'll just be next. What they always do is, well, boys play volleyball, girls play basketball. So we're not using the same equipment, and then they switch. Here it doesn't make a difference because, well, that's not true. We run practices together sometimes and we just divide the gym. Anyway, but I was reflecting on the fact that there were all these grade 10s playing who were grade 9s last year, some of whom I taught for the entire year. And then watching them play basketball yesterday, I realized oh, I haven't seen your face. And it's weird.
Basketball again.
It is weird to know somebody for an entire year and never have seen their face. And then I think half of the people in this room, well, not half, but a handful of people in this room, I've never seen your face. It's very strange. Very strange. Anyway, that's the end of my story.
I just use it as an excuse to not shave.
Yeah, you're telling me. I want to get my hair long enough so I can donate it, and then I'm going to shave. Going to shave real good. Just... Why would that go there? That's very annoying. I'm going to give you one more minute, then we'll take these up together. Yeah. Sorry? Oh, I would love to. There you go. It's Doug's door 5 years ago. Oh. My dog was horrible 5 years ago. What? Yeah, what's up? No. No, I don't know why it says that. You do not. In fact, as I understand it, your numbers have actually been lowered because of COVID. You need less. You do not need 200 hours.
Yeah, I'm done now. I need to go for 30 hours. I swear.
I like it. I almost love it. First of all, is the formula of that NaBr2 sodium iodide?
I had a friend
What charge does
doing volunteer work and
Yeah, what charge does
we just harassed Lucy and something said fucking
Good. What's the formula for this? Good. And then this is right, but would we write chlorine first and then sodium? Would we call this chlorine sodide? No. So you got the right formula. You know it's true. And then you might have to stand up if you're not careful. You might have to stand up if you're not careful. Get that product side. I might be crying as we speak. The formula's good. The formula's good. It's not that one. Yeah, draw the reaction arrow. That's important. And chlorine by itself is not just Cl. It's one of our diatomic elements. which means that chlorine isn't stable enough to have single chlorine atoms floating around. So when we find chlorine in nature, it's always Cl. It always partners up with itself. And the elements that are oxygen, chlorine, bromine, nitrate, helps us remember them. Just remember when that's by itself, that's Cl2. That looks good. Now balance it. Right, like that looks great. But now just looking on this side of the equation, how many chlorines do I have? On this side I only have. Great. So that's the number in front. Make it both balance. That's going to Yep, and that's good, but sodium is now in balance. Because how many sodiums do we have here? Nope, how many here?
Oh, you too.
Yep, how many over here? So now you have to finish that. Same thing, what's the number in front of the balance?
Did you actually take it?
Oh, no, I liked it before. I liked it better before, because bromine's diatomic. BO2. Yep.
I'm like, no.
Yeah.
Is that right?
Don't care.
Let's take a look. Yeah, that looks great.
Make yourself.
Yeah, you need to balance it now, but the compounds are perfect. Good. Balance.
Put some orange trees on.
Yep. Right. Oh, yeah, of course. Let's go.
Thank you.
No, thank you.
All the mean. You're the one who were nettles.
All right, let's take a look at these. So, when we do this first one, we have solid iron reacting with silver nitrate. That pink is too aggressive for this highlighting. That's better. Okay. So when we have iron reacting with silver nitrate, what is the chemical formula of iron? Fe. Now, is it +2 here? No, not when it's on its own. I told you when we make a compound to use +2 for sure. We'll get to that. But when it's on its own, it's not charged. You pick up a piece of metal, it doesn't shock you usually. You know, if it does, well, you know, if it's connected, if it's got a static buildup on it, or if it's like hooked up to a live electrical wire, it might. But failing that, what can we assume about this?
Solid.
Yeah, room temperature, iron will be a solid. And silver nitrate. What is, oh, I saw yours, you did silver nitride, which I didn't even notice here. So if this had said "ide," you're perfect. It actually says nitrate, so it's a little different, but good work. And yours is actually harder to work with. Silver is Ag. What charge does it take? +1. And then nitrate, which you'd see actually is a lot easier than Brie. As often is the case, you made your life so much harder than it needed to be. Did all this extra work. What's the formula for nitrate?
NO3.
Very good. And what charge does it take?
Negative.
Good. And so we can see here, I don't even need to make a table. This obviously just works. What's the formula for silver nitrate?
AgNO3.
AgNO3. Good. And we're going to assume that this has been dissolved in water. You didn't have to have that. You didn't know that, but I'm going to tell you that we would normally do this reaction in aqueous solution. If you'd written this as a solid, because ionic compounds are solid at room temperature, you're totally right. You're good. But I'm just going to tell you we're going to dissolve it in water. What's going to happen here? Like displaces like, which means that iron is going to take the place of the silver, or it's going to take the place of the nitrate.
It's going to kill silver.
Again, that's a little aggressive, but okay. Iron is going to switch places with silver. So what will be on its own on this side now? Silver. And again, silver has its dignity. It's not leaving its records behind. It's taken its electrons. So it's going to be a nice stable solid. And now iron and nitrate go together. Can I just assume that will be FeNO3?
No.
But they're switching places. Why can't I assume that?
Because Fe is +2.
Yeah, because they don't have the same charges. So I have to come over here and say, okay, silver balanced with nitrate nice and easily. Iron, not super complicated, but a little more challenging. If I just had one of each, that'd be a charge of, before you yell at me, if I just had one each, that'd be +2 and -1. Does that work? No. If I had two of each, well, that doesn't work either, but it points us at what we need. And obviously the answer is Fe2+ NO3 -1, 2. I think it is. I'm the teacher.
No, there are a
You
lot
don't
of
put the
things
charges.
that-
Okay, I don't put the charges, you're right, because they're balanced. Okay, I'm sorry, I fixed it.
32.
You also put it in brackets.
Very good. Very good. All right. So that is FeNO3(2). By the way, what would the other possible compound have been? I told you just to use this one to make life easy, but what's the other thing that might get made? Silver 2 nitrate?
It could have been nitrate.
Could have, but we'll assume the nitrate doesn't change. That's a fair assumption. Iron can be iron 2. It can also be...
Iron 1.
No, actually, iron 3 is the other big one. So we could also have had Fe3 plus and NO3 minus, in which case the formula, how many nitrates would I need to handle that 3 plus? Yeah, so this would be NO3(3). That would have been iron 3 nitrate. Both of those are possible outcomes. In practice, you'd probably get a mix of both. For the purpose of this question, we're going to stick to one. That is soluble. All nitrates are soluble. Again, you don't have to know that, so it's not like I expected you to know that, but I know that, so I'll put it there. And I'm done.
No.
Think I'm done.
To balance it.
Oh, I have to balance it. Okay, how do I balance it?
I forgot to balance it.
I have 1 iron and 1 iron. Good. I have 1 silver and 1 silver, but I've got 1 nitrate and... And my advice, guys, deal with whole ions. Like, could I say I have 1 nitrogen, 3 oxygen, 6 oxygen, you know, that? Sure. But if you've got an ion, just count the ion. Does that make sense? Makes your life way easier. So 1 nitrate, 2 nitrates. What do I do? Yep. Yeah, what do you got?
Oh, 2 in front of AgNO3.
Very good. 2 in front of silver nitrate, and
Another silver on the other side.
I need 2 silvers on the other side. Very good. And that is balanced, correct?
Yep.
Great. How's that? Not too bad? Okay. We'll do one more, then we'll talk. I don't have a lot of room here, but chlorine gas and sodium bromide, this is a nice easy one. What's the formula for chlorine gas? Assuming you didn't want me to weep openly. Assuming you didn't want to hear the bitter gnashing of my teeth and the horrible sobs of my uncontrollable sadness. What is the formula for chlorine gas? Oh, that's so good. Thank you for preventing me from sadness. Cl2, chlorine's one of our diatomic elements. We always find it in pairs. And it's reacting with sodium bromide. Sodium bromide is a nice easy one because what charge does sodium take?
1.
And what charge does bromine take?
1.
Yeah, we like these ones. So obviously that works nicely. The formula for sodium bromide is?
NaBr.
NaBr, good. And this we're just going to leave as a solid. All ionic compounds are solids at room temperature. I'm not going to dissolve this in water. I could. I'm not going to. All right, when they react, obviously I'm going to end up with sodium by itself, and chlorine takes a charge of 1, bromine takes a charge of 1, so ClBr like that, and I'll just have to balance it, right? I think I'm right.
No.
Pretty confident I'm correct.
No.
I'm the teacher.
Not anymore.
Listen, whether you like it or not, one of us is getting paid right now, guys, and it ain't any of you, is it?
It's not gonna be you either.
I'm paying you.
I get paid very handsomely to be wrong. All right, so this is not correct. Why isn't this correct? I switched. I switched. I did just what I did above. I said this switches with that.
We can take your job privileges away.
No, you can't.
Yes.
Listen, I'm well unionized. I would have to perform some act of physical violence. Oh, shoot. Yeah, what's up?
The life and yours didn't switch the light.
Good. Very good. Listen, guys, if I did what I wanted to do, I would be trying to put chlorine, which has a -1 charge, together with bromine. The problem is, 2 things that both have negative charges are going to do what?
Not go together.
They repel. That is not going to form a compound. That's not how ionic compounds work. Right?
DL.
That's an R. That's an R, thank you. So what's going to be by itself here? And assuming you didn't want me to weep, what would I write here?
But we do want.
Very good. Br2, because bromine is also a diatomic element.
I don't want you to weep, bro.
And what will the compound be? Easiest one imaginable. Sodium is now going to be paired up with chlorine. What charge does sodium take?
1.
And what charge does chlorine take?
1.
And so this is a nice easy one. Its formula is obviously...
Are there 2 chlorines in the first one?
There are,
But when you
but that has nothing to do with making a compound. Right? It is important because it's going to affect how we do what with this equation.
balance it.
Yeah, it's going to affect how we balance it, but it doesn't affect the compound. Sodium chloride doesn't know that you started with 2 chlorines. It just knows how it comes together. Does that make sense? When you come up with the formula for sodium chloride rather, that is a compound. It does not know how you made it. How you made it is going to be a function of balancing, but it's not going to be a function of what this is. And this will also be a solid. And though you are entirely correct, is this equation balanced?
No.
No, because we have 2 chlorines on the left, but only 1 on the right. We have 2 bromines on the right, but only 1 on the left. Nice, easy one to balance. What do we do?
2 in front of A, an ACl,
Yep.
and then 2 in front of an ABr.
Good. If we just get 2 sodium bromides, we can make 2 sodium chlorides with 1 chlorine gas. Good. Questions about that? We're good? All right, but you should have a question. Let's look at this one here. You should have a big, screaming, yelling question. You should be shouting at me looking at this top one, saying, Mr. Lando, there's one thing that doesn't make sense to me. One thing that I never thought about in grade 10 because we were younger then, we were silly, we were innocent, we didn't think about the difficult things in life, we just took them for granted. But now we've lived through COVID, we've come through hard times together, and now here we stand older, wiser. I mean I am neither older nor wiser. I'm as young and innocent as I ever was. But you should look at this and see the fundamental problem that is just screaming at you.
There is no problem. It's a balanced equation.
No, there is a problem. There is a problem. And I'll prove it to you.
Charges.
I will prove it to you that there's a problem.
And their signs.
Oh, it's beautifully balanced. It's a nice reaction. It looks good. So this is iron and silver nitrate, right? Okay. So let's look here. I've got iron reacts with silver nitrate. Oh, and I only need 1. Yep, so that's easy. And you tell me that becomes silver plus iron nitrate. Okay. And of course we have to balance it. So we say 2 of these, 2 of those. Okay, beautiful. Great. Love it. Awesome. Good. Makes sense. Here's the problem. What should happen if I put silver with iron nitrate? Because that's what I have now, right? Now what do I have? I've got silver sitting next to iron nitrate. Great. What happens?
Does it just switch again?
Well, talk to me. What happens? I mean, shouldn't it give me iron by itself and silver nitrate? And then to balance it, I would need 2 of these and 2 of those. Shouldn't that also be true? Which means this top one, shouldn't it just happen and then immediately unhappen? Shouldn't it? And yet, should we do this? Let's do this. Give me a moment.
You can make a lot of those, no going.
I have here some iron and some silver nitrate. How convenient. And I should get a scupula. And if I do this, what should happen to the iron? It should...
You should replace AG.
Meaning what? What should actually happen to the physical iron I'm putting in here? So here I've got some iron filings. I want to take it easy. I don't want a ton. Yeah, it should be gone, right? So can everyone see I've got the iron there? Got a little iron in there. I'm just doing a little. So I should be able to get rid of all of it. Does that make sense? And so here I've got silver nitrate dissolved in water.
Take your word for it.
I made this back in 2019. Hopefully it has not lost any of its potency. But if we leave that in there, and we just kind of come back to it in a little bit, we're going to see that that iron has dissolved away, and we get silver instead. Now, it's going to take a bit, so we're going to leave it there just kind of to chill out and do its thing, because that silver is badly rusted. In fact, that may have been a bad example. Would anyone be horribly offended if I called an audible and did this with some magnesium? Okay, give me a second.
How does this have to do with me showing you the light at all? No.
Because do you know what the first rule of doing a reaction with any metal is? Sand it, sand it, sand it so it's clean. But you know what you can't really do with iron filings? Sand it till it's clean. So that was silly. That was amateur hour. That's what that was. Because the dark stuff you see on the outside is an oxide of the metal you're looking at, and oxides don't like to react. No siree. They've already reacted. They're now nice and stable.
Yeah, let's shoot the medic. Yeah.
Oh yeah, you're not allowed to know that.
Oh, but you can already see it starting to happen. Where if you look in here, all that black silver or iron is slowly being replaced with silver. Do you see it?
Yeah.
So the iron we had that was sitting pretty and free is now actually just slowly turning into a piece of silver from the silver nitrate. Can you see that? It's all clumped together. It used to just float freely. And if we leave this in here long enough, we will just have a nice piece of silver that I could then sand down, and boom, you have a piece of silver. By the way, you might be thinking like, oh wow, that's like getting free silver, but actually silver nitrate is way more expensive than just silver, which is the problem with that particular money-making scheme. Do you see that there? It's forming a big clump of silver. But here's my question. Why isn't that immediately turning back into a big piece of iron? Why does the top reaction happen, all right, but the bottom reaction doesn't happen? And that is true, by the way. The top reaction is happening. This happens. This is true. But this one doesn't seem to happen. Why? Why do some displacement reactions happen, but others don't? What is going on? What do you know about atoms? What do you know about atoms? Whoa! $300 worth of silver nitrate I just almost dropped. What do you know about reactions? Why does the top one happen, but the bottom doesn't? What is different about iron? Yeah.
Certain metals are more reactive than others.
What a wonderful answer. Yeah, certain metals have an ability to be more reactive than others. Iron likes being in a compound more than silver does. Silver is, as a general rule, more happy to be on its own than iron. And so, when silver and nitrate are at Wendy's, and iron's hitting on nitrate pretty hard, silver's like, you know what, I like time by myself. There's worse things than being alone, and silver's like, whatever, and iron and nitrate hit it off, and they get together. Does that make sense?
Iron killed something.
But on the other hand, when silver comes up to iron and nitrate on a date, iron's like, no, I'm needy. I don't do well on my own. I think about this with myself a lot. When you get to a certain age and you have kids, you think about your own death a lot. This comes up. Sorry, it's just true. Yeah, because you have to plan for it, right? You have to write a will, and you get life insurance, and then your kids say they hope you die. All these things that make you think about your death a lot. And so I do. But then I think about like my marriage and my death, and I think that like if I died, my wife would be sad. I think. I hope. Like I think she'd be like, "Oh, I miss Joe. Like he was all right."
But anyway.
But like she'd be fine. You know what I mean? Like she'd be fine. She wouldn't miss a beat. In fact, her life would probably get a little easier. She'd probably be like, "I miss Joe," and then she'd be like, "I don't miss cleaning up after him. That's for sure. I don't miss trying to make him get places on time."
Move on.
But then I think, if she died, I wouldn't be able to find a pair of pants. Like I think of like, I don't go 6 minutes without being like, "Brett, can you help me?" And then the simplest human task. "Brett, can you help me boil water?" And she says like, "Yes, dear." And she comes like, I'm so useless. And so I am like iron. I like to be coupled. I do well in a compound, and I don't do especially well by myself. And silver is just fundamentally pretty stable. Anyway, enough about my deep-seated psychoses, but I'm just saying elements are a lot like people. Some of them are capable of doing well solo and stable relative to others. Silver is more able to be on its own than iron. Iron is more reactive. Iron needs to find something to react with to be stable, more so than silver does. And so when iron comes around and sees silver nitrate, it's a case where, full disclosure, atoms don't actually talk to each other, but silver is basically able to say, "Listen, iron, you need something to keep you stable. I'm cool, I got this, I can hang out by myself." Does that make sense? And we call this tendency reactivity, or just activity. The short answer is that a reaction will happen if a more reactive metal comes around, because a more reactive metal can always kick out a less reactive metal. Does that make sense? So for example, sodium can kick out copper. You will get copper by itself and sodium chloride. That reaction happens. But copper will not successfully kick out sodium. So we say sodium is a more reactive metal than copper. Does that make sense? The top reaction will happen, the bottom reaction will not happen. By the way, if you look at this now, you can see all the iron is basically gone. There's a little bit left on top that's like floating above the liquid, but we have basically replaced and there's a little bit on the bottom that the liquid can't seep under to, but mostly we have here now a big pile of silver. Does that make sense? Mm-hmm. And that will just keep happening if I broke that up, if I got my scupula and kind of broke it into pieces. Eventually, every last molecule of iron will find its way in a compound with nitrate, and the silver that used to be stuck to that nitrate will be solid metal there. Now, as it happens, the silver is then oxidizing and becoming silver oxide. That's a different discussion. Silver rusts. Does anyone have skin that reacts to silver? They can't wear silver because they get black on their skin? Anyone? Yeah? Yeah, so you know that experience. Some people, just that reactivity, but silver will rust, whereas you could wear gold, I'm assuming, and gold will not react with your skin, right? It's just, silver isn't very reactive, but it's a little reactive. Gold is even less reactive. So what I want you to do quickly is Google what we call the activity series. So on your device, if you have a phone, if you have a computer, whatever, I want you to look for the activity series. Because if you ever, I'm aware. Thank you. I made the note. I know what's on there. So I'd like you to look up the activity series.
Let me look out. Oh, there.
Because you won't always have lesson 2.2 note with you, but you probably, if I know you guys, will always have your phone with you.
Wow.
So I want you to take a minute and Google the activity series. See what you can find. Yeah, and it may be called the reactivity series, which is actually the language I prefer. But most textbooks and most sources will call it an activity series. But if it says reactivity, even better.
Can we do experiments at all with potassium?
Yeah, we will. So now, we totally will. So now I want to take a look, find yours online, and then I've put one on this note, and you should see it here.
Yours is
And-
a lot longer than I am.
Yeah, and I have tried to make a fairly comprehensive one here, but how do we read this? On this table, which ones of these like to react, like to be in compounds, and which ones of these are stable and don't mind being on their own and will get kicked out? On my table here, how do we read it? Yeah.
The ones near the top are more likely.
Very good. On this table, it reads as more reactive up here and less reactive down there. Which means on this table, anything higher up will always be able to kick out anything lower down. Sodium will be able to kick out beryllium. Beryllium will not be able to kick out sodium. Does that make sense? Beryllium will end up on its own. Sodium can end up as part of a compound. Getting the date. Just not functional on its own. Can't find its pants.
You?
I'm pretty useless. I have no life skills. This is just the thing. I am good at chemistry. I mean, I'm not great at it, but I'm okay at it. I'm good at math. But the other thing I think about a lot is the inevitable zombie apocalypse. I just think post-apocalyptically, when we're all wandering around fending off zombies and scrounging for food, I'm not going to last. Who needs a chemistry teacher? A chemical engineer, maybe a high school chemistry teacher? I'm going to be dinner so fast I assume I'm delicious. They're going to eat me so fast it'll make your head spin. I think about this a lot.
Bioterrorism stuff. Just chemical warfare.
You think I could figure out bioterrorism? Didn't I just tell you I need my wife to find my pants in the morning? Good Lord, I'd be like, Britt, can you help me make ricin? And she'd be like, no, I'm busy. No, I'm dinner. The zombies are going to eat me so fast. Okay, anyway. So I just wanted to ask, take a quick look. And is there anything on your list that doesn't match this one? I only mention it because sometimes different sources have minor differences, and they will be minor, but sometimes there'll be minor discrepancies, and there's a number of reasons for that. If a couple of things are switched, it doesn't even necessarily mean one is right and one is wrong. It could mean different conditions. Does that make sense? If you change temperatures, if you change pressures, if you work in different conditions, a couple of these could flip-flop spaces. And that's not the end of the world. I mention that because there may come a time when the homework, one person gets one answer, and another person gets another answer, and they say, but we both used a reliable source. That can happen. There can be minor differences. You're not going to see major differences. You're not going to find a list where strontium is less reactive than tin. That isn't going to happen. But could you find one where beryllium and aluminum were switched? Yeah, you might see that. Does that make sense?
You don't have sulfur or iodine.
Yeah, now I stuck with only the positive ions, but of course there's also...
Chlorine, oxygen.
Yes, and funny that you mention it, because isn't there just a nice little empty space over here? Oh, I wonder what I have in mind for that empty space. Maybe I want you to make an activity series of the negative ions, which is mostly your fluorine, chlorine, bromine, and iodine. So if you can make that list here and tell me what's more and less reactive there, that would be great.
Let's finish the other side of the sheet first.
Okay, so we're going to take, we're going to take 3.5 minutes and just work our way through these. Oh, sorry, not the whole thing. We're going to take 3.5 minutes and work our way through these, and then this is actually your homework. This is actually your homework. I haven't yet built into the practice app the ability to have some where the answer is they don't react. I've tried. Oh Lord, I've tried. And I've been met with sweet, sweet failure so far. Of course, yeah. Yeah, grab the device more.
You actually can do 9,000. Quick math. Yes. Why specifically 1,000? I don't even know. Usually it says 12 doubles,
Series of anions. Oh, are you saying I made a typo? That happens.
Just slightly.
Yeah. Oh, listen, I'll make many.
Activity.
I would love to never make a typo again, but this is why we have editors, team. I make plenty.
activity. I had one button. You're silly. Did you just say silly? You're silly.
Yes, that's right. I can change the cracks and make my child hand.
Yeah. Are all those computers on those tables right there, those not working?
They're a mess, but there's a ton in there. Ton in there. Chromebooks are on the bookshelf, and Windows devices are in the cart, whatever you prefer. When you go to put it back, if you don't put it back where it goes, I will injure you. That's what I'll do. Yeah. Sorry? Great, I'm going to come. First, I do want to look at these. All right, guys, real quick. What is more reactive, sodium or lithium? Yeah.
Sodium.
Sodium. Nice. How do you know?
Sure.
Higher on the chart. All right, if we look here, sodium is there, lithium is there. So sodium is more reactive. It's going to be able to kick lithium out. Copper or iron?
Iron.
Iron is correct. It's higher up. Silver or gold?
Silver.
Nice. Platinum or silver?
Silver.
Oh, we have a disagreement. I love it. Let's look.
It's silver.
That's okay, but let's look.
Silver.
Platinum is our least reactive metal. Silver is pretty unreactive, but it's still more reactive. So we're going to pick silver. And magnesium or iron?
Magnesium.
Magnesium is quite reactive. Good. Okay. We'll see after today's lab if I want to do another lab tomorrow or just the day after. Probably the day after. But in fact, why don't we just call it now? Friday we're going to do a lab. Is that cool? All right. Friday we're going to do a lab. And in that lab, you're going to make your own little activity series. Not for all the metals, because that would take a long time, but for just 4 metals and hydrogen.
What do you mean?
Well, we'll see. So I will post that tomorrow, but you are going to do a series of reactions to see whether a reaction happens or whether it doesn't. And if you tried using iron to kick out magnesium and it didn't work, you'd be able to say, okay, iron must be lower on my list than magnesium. Then when you do magnesium trying to kick out iron, it should work. If it doesn't work, then you've got a problem on your hands. Does that make sense? And you're going to do a series of reactions to make an activity series. It's kind of it's a more tricky lab. I mean, it's not physically tricky, it's very easy physically, but it's more tricky conceptually. I'm going to give you time now until block 2, but look at me. In block 2, we're doing our lab. What are we doing for a lab? Someone walk me through it. Someone walk me through it. You're looking at synthesis. Good. We're also looking at decomposition. Good. For synthesis, what are we going to do? Nice, easy one. Straightforward, yeah. Yep. And what are we going to do with the copper plate? Yep.
Oxide. Burn it.
Oh, good. Yeah, we're going to make it into an oxide. Very good. Going straight chemistry with it. Yeah, we're going to burn it. We're going to react it with oxygen. Where are we going to get that oxygen?
Air.
Yeah, just in the air. How are we going to make the copper react with the oxygen in the air? We're just going to be like, copper, react.
Yeah.
We're going to take them to Wendy's and just leave them there and see what happens?
What is it with you and Wendy's?
I like Wendy's! What's so hard to understand?
This is a Wendy's.
I I hate fast food.
Well played. I love, this is part of my problem. I love all food. If you name something that's a food, I love it.
Brussels sprouts.
Oh, are you kidding? Are you kidding? With like some nice thickly cut pancetta or porchetta or a bit of bacon and then a little bit of maple.
Brussels
A
sprouts.
little bit of maple, and you cook that with almonds, and then you finish it with a bit of a butter sauce. Oh, you can't beat it. It's like my favorite thing, but the problem is everything's my favorite thing. All of it. Anyway, I love food. Oh, I love food.
Bat soup.
What?
Bat soup.
I bet you could make it good. Don't you think? Like,
No.
here's the deal.
No.
I worked with a chef, and he used to pick the weirdest ingredients, and he'd be like, "I want you to eat this." And he'd be like, "I don't think I want to eat that." And then he'd taste it, he'd be like, "That's incredible." I never knew that I liked blank, you know? I never knew that I liked cow tongue. Turns out I like cow tongue. Who knew? Right? You just didn't know. But now I know. Anyway. Use the whole animal. If you're gonna kill something to eat it,
French people
then use all of it.
brains.
Sorry?
French people eat pig's brains.
Yeah.
People eat snails.
Yeah. Delicious.
People are weird.
I'll tell you right now. I will tell you right now. If I were to make a list of the 10 best meals I had in my entire life, I think about 7 of them were in France. And I think I only had about 10 meals in France. The food was incredible. Incredible. Oh,
Bread.
Croissant.
I love croissants.
Croissants.
Baguettes. Oh, anyway, okay. So having said that, assuming that we aren't going to wine and dine oxygen and copper with delicious French baguette and wine, how are we going to get them to react?
Heat it up with a Bunsen burner.
Yeah, we're going to heat up with a Bunsen burner. Good. Okay, I want everyone looking at it because I want to make sure when we get into lab, this is a nice, easy lab. It should take us like half a period. It should be quick. It should be clean and organized. And if we can establish that when I'm talking. If we can establish that when a lab should take half an hour, 45 minutes, we can get done half an hour, 45 minutes, and we can get lots of labs in, and we can keep them simple. And if we get lots of labs in, then I don't feel the need to make every lab a marathon of a million questions to answer. You know what I mean? We can keep them short and simple and to the point. So it's good to be ready for them, because this lab, you'll never do a simpler one. It's really easy. So we're going to oxidize copper by heating it over a copper plate, and we're going to make some good observations. Good observations. Nice, careful observations, not one-word observations. Okay, there we go. Good. What's our second reaction going to be? What's our second reaction going to be? Copper 2 carbonate. Very good. Wow, good memory. And what do we do? What's that look like? Good. Now, in a hypothetical world where your rather silly chemistry teacher spilled a lot of it, and it was no more, we don't have a ton of it, so we got to be conscientious of that. You can certainly, as a group, use everything that's back there. That's fine, but just make sure that you don't use so much that other groups are without. Does that make sense? And you don't need a ton. What are we going to do with it? Well, close. Yeah, we're going to put it in a test tube. No water. No water. No. Well, you're not going to light it on fire in as much as you're not going to put fire in the test tube and attempt to ignite the copper carbonate, but you're on the right track. We want to heat it, so we're going to put the test tube over the fire, right? And I can do that if I'm just careful to hold it like at the tip so I'm not near the flame. No, what do I need? Test tube tongs. Good. We want to get good at using those. What's our safety consideration with the test tube tongs and a Bunsen burner and a test tube?
Point it to somebody else.
Nope. Very good. We're going to make sure it's pointed away from everybody. But safety is a two-way street, always. Doesn't matter if you are pointing it away from people if people are then carelessly walking, right? So that's something to keep in mind, which is that when we're in lab, we walk carefully, slowly, deliberately. We make sure other people know where we're going. Yeah.
Don't touch it.
Yeah, don't touch it. We don't want to burn. Nobody gets burnt, okay? Please, please, nobody gets burnt. I have a 100% track record. I've never burnt somebody in lab yet. I'd like to keep it that way. I did have a kid once try to light his own pants on fire, and I even kept him from burning himself.
Why did the child...
I don't know. I just don't know.
What grade were they in?
Well, grade 10. He was in grade 10.
Yeah.
And he was being quite athletic. He had his leg like way up there. Yeah, it was, anyway, we don't want that. None of that. So listen. Good. Now, what's the other safety concern, obviously, with the Bunsen burner? We don't want to burn ourselves on the glass. We don't want to burn ourselves on the flame. What else?
Don't want to shatter the glass.
Yeah, we don't want to shatter the glass, though. If we do, God forbid, but we break a test tube, I hope it doesn't happen. It shouldn't happen. If we're being careful, it won't happen. But if it does, or if one was stress damaged and we didn't notice it and the heat causes it to shatter, that can happen once in a while. These are Pyrex, so they should survive the heat. But if one's been chipped and we didn't notice, it might shatter. What do we do in that case?
Panic.
Nope, no panic. What do we do? Hey! Not while I'm talking. Thank you. What do we do if test tube breaks?
Alert you. Guess.
Yeah, just tell me. I'll bring my dustpan and we'll wait till it's cool and we'll clean up. It's no big deal. All right, but I don't want you to deal with it because as it happens today, nothing dangerous. I mean, there's nothing dangerous in today's lab, not really. But as a good rule of thumb, when something breaks, we want to proceed as if everything were dangerous. Does that make sense? That's a good mental exercise to engage in. What's the other concern with a Bunsen burner? It's the obvious one. Even more obvious, fire. Yeah, things can catch fire. Listen, this can happen. I had a teacher I worked with, a guy named Mike Vanderperk, and he was doing a grade 10 lab with Bunsen burners. And the period before, they'd done a grade 12 chemistry lab where they'd been working with alcohols and esters. And he lit the Bunsen burner, and the bench just caught fire. Just the bench caught fire. You can't take for granted that there haven't been chemicals and things like that around. Now, that's my job. So I know that we haven't had alcohols out or anything like that on the bench. But still, you need to always proceed as if something unexpected could happen, right? So the first way, the most common way a Bunsen burner is going to cause a fire is if it gets knocked over or if something gets placed over top of it, which could be someone's hair, which could be someone's clothing, which could be whatever. So we're going to be very mindful of that. But if for whatever reason a fire were to start, what would our process be? What would we do?
Tell you.
Obviously tell me.
Shut off the gas.
The only thing I want you to be mindful of is if you are near the gas, turn it off. If you're not, just get away. Tell me. I will go turn the gas off. But whoever's nearest to it, turn it off. All right? One thing that's not going to make a fire better, gas. Right. It's not what we want. Other than that, a very safe lab, a very simple lab. But what I want you to focus on is I like to start the course with really simple labs. And I hope you don't feel condescended to. I hope you don't feel like, oh, Orlando's picking stupid easy labs. I like to pick nice simple ones so we can do a good careful job and do really well on them. Does that make sense? All right, I'll be quiet. Now, right until I won't.
I was gonna say good luck.
That stings me, sir.
Even yesterday when